Lecture 1.10 is on energy and phases. It's the new unit we're working on within large unit 1. That's called matter and energy. So we're on the third part. We combined measurement and classification into one test, and this 1C here, part again of unit 1, will consist of two tests in its entirety. So I think anyway. Any case, so we're talking about energy and phases specifically today in this first lecture of this unit. We're talking about the units, okay, of energy and what it is and the definitions. So very simply, we're going to start back to some physics here. What is energy? Okay, well, energy has been defined, okay, as the capacity to do work or the ability to do work. Now, what is work? Okay, well, work, all right, is defined in physics, okay, W is equal to a force times a distance. So work is applying a force on something over some distance, so applying that force over a distance. So how do we define that to get units? Well, we do so using SI units. Let's talk about force first. Force, by Newtonian physics, that's the physics you're going to learn first in physics downstairs, is equal to mass times acceleration. Acceleration is how much faster you're going. They have units, and we're going to deal with SI units. And the SI unit is kilogram for mass, and acceleration is meter per second squared. Okay, meter per second, by the way, is velocity. How much distance you're traveling per time, and how much distance you travel squared is how much faster you're going. It's an acceleration unit. It may make more sense to you once you take physics, but that's the unit we're dealing with for acceleration. So that's force. Distance, okay, the unit or the distance is meter. So that goes here. So when we multiply all the components of what work is, force over some distance or applying a force on an object over some distance, what we get is kilogram, meter squared, because I'm multiplying meter, okay, over seconds squared. Now some people will write it like this: kilogram, meter squared, seconds, -2. That -2 means that's on the bottom. So this is our SI unit, or System of International Units of energy, okay, or work. And it's got a particular name, okay, and this is called a joule. Notice capital. Now joule, all right, comes from James Prescott Joule, okay, so this man James Prescott, and we'll just use James Joule, okay, in 1845 did some very important work. Okay, before him there was something called the caloric theory. Okay, this theory was the idea that energy flew or traveled from one object to another in some kind of weightless gas. Okay, and through his work and some other people before him, he was the first to find a mechanical equivalent to energy. Now, what is a mechanical equivalent? A mechanical equivalent, and mechanical means motion, really. Okay, mechanical equivalent to what energy is. Okay, he was able to say, okay, let's quantify what this energy was. Now, he wasn't thinking in terms of SI units. This is what they later defined for him. So he did not come up with this. He came up with the first mechanical equivalent of energy. That's why the joule is named after him. Now, what does that mean? He was able to first take some kind of mechanical device and through motion measure a value of energy it took to do that type of motion. So before I do that, continue, let's talk about, or let me give you a picture of what I'm talking about here. All right, so I have here basically James Prescott Joule's very famous paddle, so to speak. And basically by churning this at a certain amount or a certain way, he could agitate the water. Now, he would agitate water in a barrel that was totally insulated. Again, that's probably a very almost impossible to have, but it's a very insulated container. And so this goes inside here, and he agitated it a certain way, and he measured the difference in temperature before he was mixing it violently and after, and he got a difference in temperature. In fact, what he was measuring is a foot of water. So he had a pound of water went in this barrel, and he mixed it a certain way to see what the temperature would change in a pound of water. In any case, this little crank here wasn't there. Actually, there was a pulley, and that pulley actually had a weight. And actually, what he had is a pound. And this is, of course, he was an English person, so they were using English units. So what he had here was a pulley. I'm not sure if I can write over this. We're going to try to slide. No. But let me just draw this picture. What he had was some kind of device, a paddle, and this is my ugly paddle, okay, that went into this sealed container that had a pound of water, okay, and somehow he had this spinning on a pulley, okay, into another pulley, and he had a known weight on this pulley. The idea here is the weight that he was hanging, he was going to drop it, and by dropping it, okay, and my picture is not really drawn to scale, it would actually turn and spin this, okay, spin this device and agitate it. Now, how much did he drop it? He dropped it actually a foot. Again, we're using English units, so it was a foot. He dropped the weight, okay, and he figured out exactly how many pounds it took. Okay, these are the pounds of weight it took to agitate the water so much to change the temperature of the water, okay, 1 degree Fahrenheit. Again, Fahrenheit's an old English unit that we still hold on today. So the idea was, how much weight did it take to drop 1 foot to mix the water so violently to change it 1 degree Fahrenheit? And he found that value to be 772.24 pounds, and they call this foot pounds. And again, the idea behind the foot pound was it was the first equivalent. So it takes 772.4 pounds of weight here, okay, to be dropped 1 foot to raise the temperature of water 1 degree Fahrenheit. All right, and that was the first equivalent, okay, mechanical motion equivalent. So he was able to interchangeably use the concept that motion and heat were interconnected. So the motion of the water created a certain amount of energy that raised the temperature of water 1 degree. And that was the first. Now, we don't use foot-pounds in our current system, but again, he was the first to come up with some kind of way to measure. And of course, there were other ways or other things that have been born out of this. For instance, oh, by the way, so I can finish up on James Prescott Joule, not only did he say that heat and motion were mutually interchangeable, okay, but he also stated that heat energy wasn't the only type of energy, that you had also different types like chemical and electrical forms of energy, just there's some of them that were interchangeable, and that the sum of all these types of energy, including the heat, was also conserved, and we'll talk more about that. But in any case, we have some other units that were born from this idea. The British Thermal Unit, BTU, okay, if you buy an air conditioner or freezer, any kind of energy drawing device, BTUs are often labeled. And the British Thermal Unit, the idea behind that is that it's 1 pound of water, again, it's a British thermal unit, so how much it takes to raise 1 pound of water 1 degrees Fahrenheit. And that's what a BTU is. How much energy does it take to raise the temperature of water 1 degrees Fahrenheit if you have a pound of water? Okay. And then, of course, calorie, and that came from the caloric theory. Calorie, which we all know is what we sort of use in our food industry in this country, and we'll talk more about that, is the amount of energy it takes to raise 1 gram of water 1 degrees Celsius. Okay, so that's where calorie comes from. If you have a gram of water and you raise it 1 degree Celsius, it takes 1 calorie of energy to do that, or to lower it. Okay, so these are some units. Now, a joule, we have now learned from SI units, is kilogram meters squared, okay, per second squared, okay? But its equivalent to foot-pounds is sort of interesting, maybe not. 1.356 joules, okay, I should use capital, is equal to the foot-pound. Okay, isn't that something to cherish? All right, and some other kind of interesting things. 0.000324 calories, okay, equals a foot-pound. And 1 horsepower, by the way, which is actually a power unit, that's how much energy per time, okay, but 1 horsepower is equal to 33,000 foot-pounds per second. Foot-pounds per second. Okay, so it's a time issue. Any case, that's the value. So we're going to be using exclusively joules, okay, because it's an SI, but you're also dealing with calorie in this unit as units of heat, okay, which, by the way, is a unit on one type of energy, okay, and this unit of heat, of course, is what we're going to be dealing with in our calculations. So we'll be using joules and calories interchangeably. All right, and there is a converting factor, and that converting factor is 1 calorie is equal to 4.18 joules. Okay, all right, so that's where all of that units come from. Okay, so what does this have to do with chemistry or chemical reactions? Well, chemical reactions, as we have learned, deal with, very simply, atoms being broken and atoms being reformed. Case in point, very simple reaction. I have hydrogen gas, I have oxygen gas. These are diatomic elements, okay? And they're going to make water, okay? In fact, 2 hydrogen molecules, I'm just going to show them bonded like this as models, as we've been dealing with, react with oxygen, and they form, you notice I'm going to need 2 of these. That's why I put a 2 here. Notice we've used up all of the different atoms. It's called law of conservation of mass. We'll get to that later. But in order for this to happen, I've got to break this bond. I've got to break these bonds. Bonds have to be broken. Break bonds. And of course, I have to form new bonds. Okay, as you can see. So bonds are broken and bonds are formed in chemical reactions. We already learned about that. We're always making a new substance if it's a chemical reaction. Well, my friends in chemistry, chemical bonds, the breaking of bonds and forming new ones, is all about stability and energy. Okay, what I mean by that is there's always going to be energy going in and out of a chemical reaction because we always need energy to break bonds. Always. And energy is released when we form bonds. So energy is absorbed in this case. Now I'm going to use a word, absorb, but sometimes a better word is consume. Okay, this means energy, on this side we have energy released. Energy released. Okay, now why? Why is that? Okay, why is energy always going to be absorbed when we break bonds? Why is that? Okay, well, that has to do with chemical bonds in themselves. Why do atoms bond? Atoms bond because it's energetically favorable, kind of like water flowing downhill. Or the reason, why is a rock on top of a ledge eventually going to get to the bottom? Okay, all things that are up in the air eventually do come down. Okay, why is that? Why did the apple drop from the apple tree? Okay, all those things happen because there's a lower potential energy on the bottom. So things in nature tend to go from high energy, not always, but tend to go to high energy to low energy. And my friends in chemistry, chemical bonds are a low energy scenario. The reasons why chemicals bond is collectively they use each other to become stable. We're going to learn in detail about this, but stable means low energy. So if bonds are low energy, now why are they stable? Stable means they have low energy. Well, it's a very important concept because they wouldn't become bonds unless they achieved low energy by themselves. I use the analogy. At the end of the day, when you get home from school and then your mom and your dad or whatever tells you to do your homework and do your chores, you get to do what you want to do. What do? I don't think you go outside and run a marathon. You go sit down, you lay down, you relax. We all unwind at the end of the day because we have low energy. Well, same thing with atoms. They want to use each other in a way that lowers their total energy so that they're going to stay there. Think with me. If you've got low energy, aren't you going to stay in that position for a long period of time? Yes. Low energy means you're stable. So bonding, and we'll talk more about this, creates a stable environment for these two atoms so that they have low energy. And if they've got low energy, my friends, they're not going to do anything. They don't have the energy to do something. So strong bonds, okay? And I think I'm going to go to another page here. All right, strong bonds always give you very stable. All right, so if we go idea here, so strong bonds equals stable atoms. And weak bonds give you unstable. So if you've got a weak chemical bond, that means it's unstable, which means it's going to do something because it has high energy. Stable compounds have low energy. They're going to stay in that position because they don't have the energy to change that. That's a very important concept. So stable atoms. Now, the thing is, not all chemical bonds are the same. We do know this, though. Atoms that are not bonded, like pure hydrogen, are unstable. They're highly reactive. They're going to do something and chemically react. Why do things chemically react? To achieve stability, to get lower. Why does a rock on top of a hill go to the bottom? Because it's energetically favorable. So these bond. And guess what? Energy is released. Okay? Energy is released when that happens. So back to my reaction. Okay, where I have two H2s reacting with an oxygen to make two water molecules. Okay, this is a chemical reaction, and if we are to evaluate the energy it takes to break these bonds, let's just pretend it takes this much energy. Let's make some joules here. Let's make it takes 100 joules to break all the bonds. Now, it should make sense to you why it takes energy to break these bonds. Because I'm breaking a very stable, low energy scenario. It takes energy to break bonds because it takes energy to give them so that you have the energy to do something. Or think with me, to break something, it needs energy. So when 100 joules, so I'm going to start with, and I'll change the, I'll start with H2 and O2. Okay, now, it takes energy. Energy is absorbed, okay, or consumed. All right, oops, edit, undo. Okay, and then we'll change the ink again to red. Energy now is released. Ooh, that didn't work out too well. Energy is released when you form new bonds. So I'm going to go down. This is energy released. Let's pretend it's, I don't know, 200 joules is released. Notice I'm going down. Energy is going down. Notice I can't spell released. All right. So energy is released. So my friends in chemistry, it took this amount of energy to break these bonds. And then when they reformed to make a very stable compound, in this case, 200 joules was released. So we started at a certain value. We ended at a lower value. So if you look at it, water is more stable. If you look at this graph that I just kind of made, this is a graph of energy, potential energy. Energy of the compounds. This is potential energy. And look at this. Because more energy was released, we're going to say that there's an overall loss of energy. The difference of where we start and finish is the change in heat. And notice it went down. It went down by 100, right? Went up 100, went down 200. So the overall net change is negative 100 joules. And we say the delta H of this reaction is negative 100, okay, joules in this case. What does that tell me? Well, how did I lose more energy than I had? I must have released. This is an exothermic reaction. Notice the word exo. Heat is exiting. Why is it exothermic? Heat was released. Okay, and what we do in chemical reactions is we write the heat on the product side. So this would be 100 joules. Notice it's positive. Heat's positive, but my delta H, okay, is negative because it shows a change. All right. Now, what if I go in the opposite direction? Okay. What if I change things around? So what if I had water, okay, which, by the way, is pretty stable compared to H2. I'm just kind of drawing this in backwards, H2 and O2. So notice it takes this much energy to break bonds and not so much energy to reform bonds. Notice H2 and O2 are more unstable. I'm kind of compacting this drawing. Oops. I'm trying to compact in this drawing here. What's the difference now, where we start and where we finish? Okay, if you notice, it's positive. We started here, and now we're going up. So we're going up 100. This would be positive, right? What's the value? It takes 200 joules to break these bonds, and only a minus or 100 joules it takes to form new ones. Clearly, H2O2 is unstable, and that makes sense. We're making something unstable. These were unstable. That's why they had so much more what? Energy. Look how much higher they were. Okay? So in a chemical reaction, energy is always absorbed and released, but the net change is how we evaluate who got absorbed or how much got absorbed and how much got released. So back to the example below here, which is the same, just in reverse, the delta H, or the change in heat, is positive 100. And this is endothermic. What does that mean? That means if I have a chemical reaction and I have my two waters going to two hydrogens, again, balancing these coefficients are not important here, I need to put the energy on the reactant side. For those that didn't know, and I'm sorry, these are your reactants. It's what's going to react to make products. So these are the reactants. These are the products. Okay, so we place the overall net change into the reaction to show if it's endothermic. Endothermic means energy is absorbed or better yet consumed. And I keep saying better yet consumed because it doesn't take in the energy in itself, get warmed. It takes in the energy and uses it to do what? To make something unstable. Think about it. I'm making something more unstable than what I started with. It takes energy. This is like making a bomb, making explosive. And the one above it, which is the opposite, okay, is like lighting off the explosives, okay? So this is clearly the most unstable or weakest bonds, and this has the strongest bonds. Notice water is pretty darn stable. It's got strong bonds. That's why it takes the most energy in the reverse to break. And it's a good thing water has strong bonds and stable, because we need water in our environment. We don't need it to break down. We wouldn't have oceans of water, okay, in our environment if it wasn't stable. But we do not have oceans of hydrogen and oxygen, all right, which is highly explosive, which means it's unstable. Okay, so we place the energy. So I want you to understand that when we're doing endo and exothermic reactions, we're placing the energy, the heat, on the reactant side if it's endothermic. We're placing the energy or the heat on the product side if it's exothermic. We're producing heat. Heat is exiting. It doesn't mean that there's only one energy change. It just means if something is exothermic, there's more energy released in forming these stable, strong bonds that it takes to break them. Both things are happening, but this is the overall net change. Okay? Endothermic means energy is being consumed, taken in, or absorbed. Notice it's on the reactant side. The reactants need it. Exothermic, again, I can't say it enough, energy is being produced. Now, chemical reactions are not the only processes or, that use these heat flow. Phase changes. Think with me. A solid and a liquid and a gas. And I say gas because they have tremendous energy. Gases have more motion than liquids. Liquids have motion than solid. So if you want to melt a solid or boil a water to make these phase changes, it takes energy. So these are endothermic. All right? And if I want to go from a gas, tremendous energy, down to a liquid, condensation, or down eventually to a solid, freezing, how do you go from high energy? Notice I'm still drawing that kind of graph. This is energy. How do I go from high energy to low energy? I do so by releasing it. So going down in energy means energy had to be released into the environment, which means you're producing. So how does a gas become a liquid? It loses the heat. The heat is given off as a product. And we say going to a gas to a liquid to a solid, it's exothermic. All right? As one, and I'm going to leave you with that understanding today. Okay, it's a lot to grab, and that's part of the form. All right. So again, we have some very, very important understanding what energy is. It's the ability to do work. We measure it by some very important units, and we have joules. Okay, calories, and those are the two we're going to use. Now, I guess I want to end on one little important piece. If I was to go to a reference table, and I'm giving you table I, and again, we're going to do this much later, but here's table I. Look at delta H here. This is methane combusting. These are combustion. These are burning reactions. Look at, they make CO2 and water. Why is delta H negative? Energy was released or absorbed. Well, if you forget, the reference table, which by the way is part of the New York State curriculum, they even tell you minus sign exothermic. As I just taught you, a minus sign tells you what? The reaction is exothermic. This must be more unstable than this. So delta H, or the change, is going down. Why is it going down? So you're starting high and you're going low. The two differences. So these guys are your reactants, and these stable compounds, oops, I don't know what just happened. Sorry. Stable compounds are your products. And the difference of where you start and where you finish is this. It went down. This is the energy release. These guys have all this energy locked in. Now notice the ones that are, by the way, CO2 is very stable, isn't it? It better be stable because it's got to get back to the plants to convert back to oxygen. Okay, so these are important concepts. So notice very stable products. It means these bonds are stronger. These bonds are weaker. These are unstable going to stable. Now, if you look on table I, most of the reactions are negative, but there are some positives. Look at this. I'm making a hydrocarbon here. Hydrocarbons can be burned off, so I'm kind of making an explosive here. Notice the delta H is positive. We're making something unstable. Another example of a hydrocarbon we're making. This positive means that we're starting with something stable and we're making something unstable. We're going up in energy by that much overall. Okay? Any case, we're done for this now. Hope you finished the form out. Plenty of different concepts here. Please rewind this and listen to the differences or the things that I said here. Okay.